Okay, so in this lecture, I want to go through methods for synthesizing carboxylic acids. Now, it turns out we've already talked about some approaches for synthesizing carboxylic acids, and that is oxidation protocols, where we oxidize aldehydes. So we could take an aldehyde, which is this functional group here, and we could do an oxidation reaction, which I'll abbreviate with an O in brackets, to get our carboxylic acid through an oxidation process that leads to the addition of an oxygen atom. Now, a classic way of doing that is the Jones oxidation, so H2Cr2O7 in some form. Okay, I'm going to move Jones over here. That's a weird place to put it. Okay. And what that does is that just right away converts our aldehyde over to a carboxylic acid. And in fact, we can use this protocol to convert primary alcohols to carboxylic acids, and they proceed through the aldehyde. But if you remember, they don't stop at the aldehyde. We have to use a special chromium reagent to do that, and that gives rise to the carboxylic acid. Now, nobody, well, I shouldn't say nobody, but the number of people that are doing that are converting alcohols to carboxylic acids in the world, that's a big number. A lot of people are converting carboxylic alcohols to carboxylic acids. That's a really important transformation. But the number of people that are doing them with the Jones oxidation reagent versus some Grignard protocol is very small. That is, most people are doing this in a very green process. It's not too hard to do with some sort of bleachy type reagent and primary alcohol. Now, I know we saw that bleach didn't actually convert it, but the thing I want to get across here is people aren't using Jones oxidation, but they are thinking about this transformation. And so that's what I like. That's why I still like to show this old school transformation, is because not because I expect you all to go and grab the Jones reagent, but I want you to think about a way to make carboxylic acids is through an oxidation of an alcohol. Anyway, moving on. So that's a process we have seen before. What about one we haven't seen? So it turns out that a really versatile way to make carboxylic acids is through from the nitrile. So the conversion of nitriles to carboxylic acids works really well. We've seen this with the Strecker reaction, but we didn't look at it in much detail. What's cool about it is you can use either H plus or OH minus. So you can use strong acid or strong base as long as both of the conditions use water. Okay, so what we do in this case is we take a nitrile and we treat it with, well, let's do it this way. Let's do plus H2O. So this is considered a hydrolysis reaction because we break the nitrile to make a carboxylic acid in this case. If we do a little bit of highlighting here, this carbon that's triple bonded to the nitrogen that's just shown by the break in the lines, that's what ultimately becomes the carbonyl carbon. And then the oxygen from the water is what gets added to the carboxylic acid. Well, I should be careful there. Okay, let's just stick to let's make it simple. Okay, anyway, we can use either H plus or H minus to facilitate this reaction. Now, I suppose an important thing is that if OH minus is used, we finish with the carboxylate. But a lot of time, I just want to make note of that. If we have some base around, we're going to do an acid-base reaction and make a carboxylate. But let's say we protonate things during workup. So we do some sort of workup where we add a bunch of H plus, not to facilitate the transformation, but to just get us to a neutral carboxylic acid when we're all said and done, and get rid of our excess base that's lying around. Okay, so we can use either H plus or OH minus. Now, with that in mind, what we should do is look at the mechanism for the mechanism for nitrile hydrolysis . with H plus or base is going to look like this. Okay, let's start with base. That one is, I think, a little bit easier. Okay, so with base, what we do is we first recognize that a nitrile is has got a carbonyl embedded within it. So we can actually consider a resonance structure. We're not going to move atoms too far, but we can consider resonance where we have a negative on our electronegative element, a positive on our electropositive element, which is carbon in this case. Now we can see what an OH minus might want to do. It will engage that carbon that's triple bonded to the nitrogen. You could use either resonance structure to show the outcome, but we're going to end up with a carbon-nitrogen double bond, nitrogen with a negative charge, and then an OH adducted. Okay, now it's at this point that we probably see a series of deprotonations, or just a single deprotonation. A deprotonation here, and that's going to give us this species, which is highly unstable. We don't even need to show base adding here. Hydroxide. We could just have neutral water. I'm going to consider a resonance structure where I push the carbon nitrogen electrons up. It's very stable. Positive charge because it's surrounded by two atoms that are willing to donate electron density in. So this isn't going to be, well, it's pretty reactive. It's a pretty favorable process. The oxygen is going to add into the positive charge. Kind of saw this with the Fischer esterification, except for under basic conditions. Okay, deprotonate again. And so with a species like this, what we're going to see is a favorable process that leads to the ejection of ammonia. So this is not great, but what I would recommend is let's just have the nitrogen reach over, grab the O, and then push off the, grab the hydrogen that's attached to the O, push down to make it carbon-oxygen double bond, and that's going to give rise to our carboxylic acid plus ammonia. Very favorable process. Okay, so we use this kind of thing in the Strecker reaction to convert nitriles into carboxylic acids, which ultimately gave rise to our amino acids that we saw with that Strecker reaction. The Strecker, let me articulate that more clearly. Okay, I haven't thought about the H plus mechanism in a while, but it's very similar, except we now have no OH minuses around. We rather have H plus. So if we protonate first on the nitrile, we get a positive charge on that carbon-nitrogen double bond. The oxygen is going to be, oxygen from water is going to be poised to attack into, and we're going to start to launch into the same series of events that we just saw. Only we've got an abundance of H plus lying around. And so what I'm going to do is just let the H plus fall off the oxygen. Then I'm going to protonate the nitrogen of our imine just to speed through this mechanism because we've kind of done all this already. So that's going to give us this. And now water is going to add in. So we saw this last time. It's just now everything has like got an extra hydrogen and an extra positive charge, but we're going to get to the same species where we just have a ton of heteroatoms on a single carbon, and the nitrogen, being basic, is going to pick up hydrogen to make for an excellent leaving group, which is NH3. and then we could lose a hydrogen, push off NH3, and that's going to give our carboxylic acid our proton from our strong acid, and that proton will likely be buffered by the NH3 that's being generated. So it's harder to do this thing under catalytic conditions. Okay, so we went through two mechanisms pretty quick. I don't like to test people too hard on these mechanisms because there's so many other ones that are a little bit more useful. But what I want you to know is that nitriles are a really good entry point into carboxylic acids. And so making nitriles isn't too hard. Is easy's making nitriles is can happen. There we go. That's articulation for you. Okay. Making nitriles can happen. I'll just write, it's easy. It's easy. It really is. It's easy to make nitriles. Okay. We've seen these things before. You can do the Strecker reaction, cyanohydrin reaction. So this is a pretty versatile entry point into carboxylic acids. You can even do SN2. Now, an issue with all of these is they require toxic cyanide sources, okay, which obviously is a downside. But on paper, it's fun to talk about, okay? And if you're safe, it's fine. But like an SN2 reaction would be where we take some cyanide salt and we just add it to an alkyl bromide, do an SN2 reaction to give. Be careful not to lose carbons in that structure, but there's a nitrile. Okay, so we can do these types of things. And then we went through the Strecker reaction in previous lectures, so I won't go through that. Okay, now what I want to end with, sorry to rush to get here, but I just really like this reaction, is we can using organometallics. I just love this reaction. Using organometallics with CO2 to make carboxylic acids. Okay, the way this reaction works is in organometallics. Let me clarify what that is. That could be our Grignard reagent or something like a Grignard reagent. You can use an organolithium, all the stuff we haven't really talked about, but I'll focus on the Grignard reagent. Okay, so if you recall, a Grignard reagent is this, and it's basically an R- that can add to some sort of electrophile somewhere. Now, what's the go-to electrophile for a Grignard reagent? Or it's a carbonyl. Well, what's carbon dioxide but two carbonyls? And so what we can do is we can just add the R group to the carbonyl carbon, push electrons over, and we get to this species, which we then just add some H plus to work up, and we get a carboxylic acid. Goodness, I love this reaction. I like it so much because it uses carbon dioxide as a C1 building block, as a single carbon building block. I mean, we have a huge problem with a huge abundance of carbon dioxide, but we have a huge need for organic molecules to be made to better living through chemistry, improve the quality of a human's life. So it would be great if, both the problems could collide into a massive solution where we can figure out technologies that take advantage of all of the C1 building blocks up in the atmosphere, and we start assembling our massive molecules like Legos, where we just have a lot of like single carbon building blocks that we can attach to each other. So I think this is a great starting point, or just a great approach, just using carbon dioxide as the C1 source. It gets trapped, it's built into the molecule through a carbon-carbon bond already, and we make a very useful functional group from an overly abundant molecule in our atmosphere. Anyway, exciting stuff. Hopefully you enjoyed that, the way we've ended that one. But otherwise, that'll do it for this lecture, and then we'll get back into actual reactions that carboxylic acids can do next time. Okay, so until then.